Hello, this is a short lecture on our Sun. There are several layers in the Sun. In the center we have the core. This is made up of gas 15 million degrees Celsius. Because the temperature is so high and the pressure is so great, this is where fusion is occurring. The next layer out is the radiative zone. Here energy moves from atom to atom in the form of electromagnetic waves. This zone is 2.5 million degrees Celsius. This is where the radiation is coming from in the Sun. The next layer up is the convective zone. Here energy is transferred through convection, so we have these convection cells. The next layer is the photosphere. Photo is a root word meaning light. So this is the area of the Sun in which visible light is generated and given off. This layer has a granulated look, looks like it's bubbling. The next layer out is the chromosphere. Chrome is a root word meaning color. This is the layer of the Sun that gives the Sun its color. It glows red. The next layer out, the last layer, is the corona. This is the outermost layer. This is a huge cloud of gas heated by the Sun's magnetic field. The Sun's magnetic field and the corona prevent most of the atomic particles from escaping to outer space. Sometimes ions can stream out into outer space through holes in the corona. We call this solar wind. Okay, let's label the layers of the Sun in the diagram. Let's start in the center and work our way out. So the center is the core. The next layer out is the radiative zone. This layer gives off a lot of the radiation that the Sun generates. The next layer out would be the convective zone. This is the layer that we have convection cells. The next layer out is the photosphere. This is the layer of the Sun that gives off the light. Photo is a root word meaning light. The next layer out is the chromosphere. Chrome is a root word meaning color. This is the layer of the Sun that gives it its color. And the final layer is the corona. If you've ever drawn a sun, the little lines you draw outside the Sun, that is representing the corona. Fusion is when two atomic nuclei are combined. So the Sun fuses hydrogen, so it takes two hydrogen atoms and forces them together to create helium. Red giants will fuse helium. The Sun is currently a main sequence star and fuses hydrogen. Next it will become a red giant. Currently the Sun has about 74% hydrogen and 25% helium. This tells us that the Sun is about halfway through its life. Sunspots are cool, darker areas on the Sun. In this case, gases are rotating at different speeds throughout the Sun. The gases are rotating in convection cells. Both of these movements are created by the Sun's magnetic field. However, the Sun's magnetic field will slow down the convection cells. This will result in the top of the convection cell getting cooler because it's farther away from the heat source for a longer period of time. This will create the dark areas on the photosphere. Sunspots can reach up to 100,000 kilometers in diameter. This is several times the size of our Earth. So here's a close-up image of the Sun. Here are your sunspots. Remember, these are several times the size of our Earth. Sunspots increase and decrease in a cyclical pattern. The cycle repeats itself every 11 years. If 2008 was our last sunspot minimum, are we currently in a maximum or a minimum? The Sun's magnetic field can cause superheated gas to arc out over the surface of the Sun up to 500,000 kilometers in outer space. These prominences follow the Sun's magnetic field, and they can last up for weeks or even years. To give you an idea about how big these really are, here's the approximate size of the Earth. You'll notice they follow this arc-like pattern. That follows the Sun's magnetic field. The Sun can also produce solar flares. Solar flares are violent eruptions that can send ions out into outer space. Remember, ions are electrically charged particles. Solar flares can extend several thousand kilometers within minutes. These don't last nearly as long as prominences last. These last up to an hour or two. Solar flares have been associated with sunspots. So if we have a maximum number of sunspots, we're going to have more solar flares. Here's an image of the sun releasing a solar flare. This image has a filter on the camera so we can see the solar flare easier. Here's where the eruption takes place, and you can see the streams of particles and ions flying into outer space. The biggest of these eruptions are called coronal mass ejections. Sometimes you'll see this shortened to CMEs. These are caused by the shifts in the sun's magnetic field. Because the sun is made up of gas, its magnetic field can get twisted, much like a spring would get twisted. Well, sometimes these get twisted too tight, and when they release, the coronal mass ejections are released. These are strong enough that it can disrupt radio signals and transmissions. They can cause blackouts. They can damage satellites in orbit. They can even harm astronauts that might be outside of the space station at the time. Here's a live image of a coronal mass ejection that happened in 2002. This white circle you see is the surface of the sun. This big red band, that's just a block that they put on so we can see the coronal mass ejection a little bit better. You'll notice that it takes a span of about 4 hours. Within those 4 hours, you can see the eruption getting much larger than the sun itself. One neat phenomenon that we get from solar wind hitting the Earth are auroras. These are your northern and southern lights. When the solar wind strikes the Earth, the ions travel to the North and South Pole because of the Earth's magnetic field. When those ions reach the atmosphere, it'll excite the atoms in our atmosphere, producing the lights. The most common northern light is green. The second most common color is red. Why is this? I'll give you a hint. Here's your hint. These percentages should sound familiar to you. 78% and 21%. The answer is 78% of our atmosphere is nitrogen. Since this is the most common gas, we see green. Nitrogen will produce the green color. Oxygen will produce the red color. That's the second most common atmospheric gas in our atmosphere. Here's an image from outer space. This is the northern lights surrounding Antarctica. You see how it's mostly green. Here's another image. You have some green down here, and you have some red up here. Here's the Aurora Borealis over Norway. So again, you see the most common color is green. Here's a diagram to show you what's happening. So the solar wind comes off the sun and hits the Earth's magnetic field. These lines here represent the Earth's magnetic field. The Earth's magnetic field will then transport some of these ions to our north and south poles, creating our northern and southern lights. This concludes the lecture on our sun.